Okay, we finally arrived at the calculus of residues. This is an area that is one of the reasons why complex analysis connects to so many other fields in mathematics, because in many fields of mathematics you end up having to solve certain kinds of integrals, and if you want to do the theory, you want to have an exact answer for those integrals, and a lot of these integrals are being solved through the calculus of residues. As we are going through these computations, you will see that the calculus of residues is a beautiful mix of argumentation, estimates, visualization, as well as computation. As such, however, it is also rather demanding, so I would recommend after every single example, take a look at some homework problems that may be similar and see if you can do those computations. That's what the pause button is for. The whole presentation, I think, will take quite a while, and we might even cut it up into two pieces. The integrals themselves, you may ask yourself, well, how on earth do people come up with those things? And it turns out that even though the background is, of course, hard to see when you are, quote-unquote, just learning complex analysis and calculus of residues, I think just about every example and just about every exercise in a section on calculus of residues is an integral that ultimately arose in some application where people wanted to have, or where people needed the exact answer for that integral. It just isn't listed where exactly the integrals are coming from. Okay, let's take a look at what we want to do here. So the calculus of residues is the computation of regular as well as improper integrals on the real line. We will, for the most part of this presentation, talk about improper integrals, except the last section on the sines and cosines actually will also deal with some regular integrals, integrals that go from one point to another point. And we're going to compute those integrals by using contour integrals in the complex plane. And that would certainly sound preposterous without further information, but we know from the residue theorem that integrals over closed contours can be computed as a sum of residues, which means even though an integral in the complex plane feels harder than an integral on the real line, well, in the complex plane we have a tool that we do not have on the real line. So that means if we use contours to that include the appropriate part of the real line for the integral, and then somehow get rid of the part of the contour that is off the real line, well, then we have a new way to compute definite real integrals and improper real integrals, and that's exactly what's going to happen here. For improper integrals, we will need, of course, a limiting process, but that then just means, that the part of the contour that is off the real line will somehow have to be sent to infinity also, and we'll see in the examples how that goes. Okay, let's first take a look at some of the pertinent definitions. The improper integral of a function f from 0 to infinity is the integral from 0 to infinity f of x dx, which is the limit as the upper bound r goes to infinity of the definite integral from 0 to capital R f of x dx. The improper integral of f from negative infinity to 0 is analogously defined as the limit as the lower as r goes to infinity of the integral from negative r to 0 f of x dx. The improper integral of f from negative infinity to infinity is the integral from negative infinity to infinity f of x dx, which is the limit as r1 goes to infinity of the integral from negative r1 to 0 of f, plus the limit as r2 goes to infinity of the definite integral from 0 to r2 f of x dx. Now, what's very important about this definition is that both these improper integrals from negative infinity to 0 and from 0 to infinity must exist separately. That means we cannot have any cross cancellations from stuff on the left side of the y-axis with stuff on the right side of the y-axis. And that is important because there is another notion of integration, which is the Cauchy principal value of the integral from negative infinity to infinity. And we will denote that as PV integral negative infinity to infinity f of x dx, which is the limit as r goes to infinity of the integral from negative r to r f of x dx. Now here we need to be a bit careful, because in a lot of texts, definitely in a lot of applied texts like physics and engineering texts, but also in quite a few mathematics texts, the notation integral negative infinity to infinity f of x dx is also used for the principal value, and we're going to see conceptually the principal value is something entirely different from the improper integral. And in fact, the first thing we're going to do is we're going to look at the connection between principal values and improper integrals. So, proposition. Take a function that's defined on the real line, and if the improper integral from negative infinity to infinity exists, then the Cauchy principal value exists. But if the Cauchy principal value exists, the improper integral need not exist. So how does that go? Well, first suppose that the improper integral from negative infinity to infinity exists. Well, then the principal value is the limit as r goes to infinity, negative r to r f of x dx. And that, of course, because these individual limits exist, can be broken up into the limit as r1 goes to infinity integral negative r1 to 0 f of x dx, plus the limit as r2 goes to infinity integral from 0 to r2 f of x dx. And that would be the improper integral from negative infinity to infinity f of x dx. On the other hand, the principal value of the integral from negative infinity to infinity of x dx, well, that's the limit as r goes to infinity of the integral negative r to r x dx. And because this is an odd function integrated over a symmetric interval, these values are all 0, so the principal value is 0, whereas, of course, the improper integral of f of x equals x from negative infinity to infinity does not exist, because we've got infinite area to the right of the y-axis and infinite area to the left of the x-axis, and improper integrals, as I said, don't allow for these kinds of large-scale cancellations. Okay, there is a bit of a connection, and that is between improper integrals and principal values, and that connection exists when our function is even. So it's very important here that that only works for even functions, because if the Cauchy principal value for an even function exists, then the improper integral from negative infinity to infinity also exists, and we have that the principal value is equal to the improper integral, which is equal to twice the improper integral from 0 to infinity. And in order to do that, well, let's just remember that the principal value is the limit as r goes to infinity integral from negative r to r f of x dx, and we know that that exists, but because the function is even, that's also twice the limit as r goes to infinity from 0 to capital R f of x dx, and that's twice the improper integral from 0 to infinity, which we would have up here, right? So therefore the improper integral of f from 0 to infinity exists, and it also satisfies the equality that this part here is equal to this part here. Sorry about the bad highlighting. I have not figured out a way to make that work better. But because f is even, that means that the improper integral of f from negative infinity to 0 exists too, because after all, for an even function, that integral is the same as the one for from 0 to infinity. And that means that the improper integral of f from negative infinity to infinity exists, because that's just the sum of those two improper integrals. And we have that the integral from negative infinity to infinity f of x dx is twice the integral from 0 to infinity f of x dx, and that was the principal value. So we have that all these identities up here all work out. Okay, yeah, that's the principal value. Okay, I think now, now we're still going to talk about some general theorems before we're going to look at concrete examples. One of the things that often happens is that you want to integrate certain rational functions, and of course we can do that using partial fraction decompositions, but these partial fraction decompositions can get rather hairy, And so let's take a look at this. If P and Q are real polynomials without common factors, so that Q has no real zeros, that's something we have to be careful with for a while. We will specifically consider the idea that we have poles on the real line separately. And so that for every semicircle of CR of radius r centered at 0 and contained in the upper half plane, we have that the limit as r goes to infinity of the integral over that semicircle of the rational function p over q dz is equal to 0. We let z1 through zn be the zeros of q in the upper half plane. Then the principal value of the integral of p of x over q of x is 2 pi I sum k equals 1 to n of the residue of f at z equals zk. Let's see, and in most of our exercises, in most of our examples, except when we get to the end of the branch points and branch cuts, we will typically focus on the upper half plane, and that is because typically, even though it is not necessary, typically our functions will be real functions that spit out real values, and that means that by the Schwarz reflection principle we realize that anything that happens in the upper half plane happens with the appropriate conjugations in the lower half plane, and that means we really can concentrate on the upper half plane throughout. Give me just a second here. I didn't say that f was equal to p over q, so let me fix that typo there. Okay, we're back, and the typo is fixed. Let's take a look at what we're doing there. Basically, what we're interested in is an integral on the real line, and we want to close that integral up. And so basically what happens is we're interested in the integral on the real line here from a value negative r to a value positive r. In order to turn that into a contour, we close it with a semicircle. And because we let r go to infinity, the most natural thing to do is then to just let the size of that semicircle go to infinity also. And the hypothesis that we have in this theorem that we're about to prove says that the integral of the function over this semicircle goes to 0. And if that's the case, well, then that means that the limit of these contour integrals really is the Cauchy principal value of the integral on the real line, because after all, the residues will ultimately, as the circle is large enough, give us what the integral over the contour is, and then as r goes to infinity, the integral over the circle goes to 0, and the integral on the real line goes to the Cauchy principal value. Now we have to be careful here. It really is the Cauchy principal value because we are going across a symmetric interval. That just means that if we're actually interested in the improper integral, we would need to use a separate theorem to establish that the Cauchy principal value really is equal to the improper integral. That being said, let's go ahead and prove this result. For r large enough, we have that the residue theorem gives us that the integral from negative r to r, p of x over q of x dx, plus the integral over this circle that closes the contour of p of x dx. I probably could have said p of z dz, but it really doesn't matter what we call our dummy variable. That's 2 pi I times the sum of the residues in the upper half plane, because ultimately, if the radius is large enough, all the residues in the upper half plane are inside that semicircle. So that's just a straight application of the residue theorem. Now we let r go to infinity, and by assumption, the integral over CR goes to 0. That's this assumption up here, right? And the right side, of course, is constant. Once we've captured all the residues, there's nothing happening here anymore. And that means that the principal value, which is the limit of this as r goes to infinity, is 2 pi I times the sum of the residues of the quotient p over q in the upper half plane, and that's already it. So the theorem isn't that difficult, but it's a good starting point in this very typical idea that you take an interval on the real line and you close it with a complex contour, and semicircles are often the most typical ones. Every so often you use something like squares or rectangles. I don't think we're going to mess with those too much in this presentation, but that's something that you might also run into. Okay, so let's take a look at an example. We want to compute the improper integral from 0 to infinity of 1 over 1 plus z to the 4th dz. Well, we have that the integral, and this thing is, let's see, this thing is an even function, which means computing the Cauchy principal value will be okay. We then just have to divide it by 2 to get the integral from 0 to infinity, as long as the Cauchy principal value exists. So we start out by just applying that theorem. If we integrate this function over a circle of radius r and take the absolute value, well, then we can just pull the absolute values inside and integrate against the arc length. That's something that we've done a couple of times now. And that is less than or equal than the integral of 1 over z absolute value to the 4th. That's because z to the 4th plus 1 will be greater than or equal to z absolute value to the 4th. This stuff will be greater than or equal to r. That is correct. And that means that the if you do the reciprocal, then 1 over this thing will be smaller than 1 over z to the 4th, z absolute value to the 4th. And of course, now if we integrate against the arc length over a semicircle, we get that the integral is pi r. And on the circle of radius r, the integrand has value 1 over r to the 4th, so we get 1 over r to the 4th, and that's it. And that, of course, goes to 0 because that's pi over r cubed. Okay, and that's as r goes to infinity. Okay, so that means we can apply the preceding theorem. So let's take a look at the zeros of the denominator. We now just need to find the residues in the upper half plane. So 1 plus z to the 4th equals 0 gives us z to the 4th equals minus 1, which is e to the I pi, which means that z is e to the I pi over 4 plus the integer multiples of I pi over 2, which is ik pi over 2, where k goes from 0 to 3. And now only the zeros z1, which is e to the I pi over 4 when k is equal to 0, and z2, which is e to the I 3 pi over 4, are in the upper half plane. When k is equal to 2, we end up with e to the I 5 pi over 4, which is underneath the x-axis, and when k is equal to 3, we end up with e to the I 7 pi over 4, which is also below the real axis. So only these two are in the upper half plane. And because this thing has 4 distinct zeros, that means that every singularity of 1 over 1 plus z to the 4th is a simple pole. And in the previous presentation, we've seen that the residue at simple poles is, if you've got a numerator and a denominator, then the residue is just the numerator divided by the derivative of the denominator at that singularity, and of course we're going to use that. So the residue at z1 equals e to the I pi over 4 will be, well, numerator is kept, denominator is differentiated, 1 over 4 z cubed at z equals e to the I pi over 4. Just plug that in. We end up with 1 over 4 times e to the I 3 pi over 4, if you will. And I think I'll put that in the numerator. Yeah, that's 1/4 e to the negative I 3 pi over 4. And now we turned it into rectangular form. E to the negative I 3 pi over 4. You start on the real axis. You go 3 pi over 4 around in the mathematically negative direction. That means we end up in the 4th quadrant on the diagonal, and so that means e to the negative I 3 pi over 4 is actually negative 1 over root 2 minus I times 1 over root 2. The 1/4 is kept, and if we factor out the negative 1 over root 2, we end up with negative 1 over 4 times root 2 times 1 plus I. The residue at e to the I 3 pi over 4 goes the same way. We take the residue, which means we take 1 over 4 z cubed at z equals e to the I 3 pi over 4. We plug that in. We end up with 1 over 4 e to the I. That would be 9 pi over 4 ultimately, which we can put in the numerator. And that would mean it's e to the I negative 9 pi over 4. And that's the same as e to the negative I pi over 4, because 9 pi over 4 is of course 8 pi over 4 plus pi over 4, and the 8 pi over 4 is a 2 pi that doesn't do anything in the exponential. Still have the 1 over 4 here. This is something that's in the fourth quadrant, and so we end up with this being in rectangular form. 1/4 is being kept. 1 over root 2 minus I times 1 over root 2. Taking out the 1 over root 2 gives us 1 over 4 times root 2 times 1 minus I. And if we now want to have the improper integral, well, that will be 2 pi I times the sum of the residues. Actually, we have to multiply that by 2. Hang on just a second. And we're back. Yeah, the integral from 0 to infinity is, of course, 1/2 the integral from negative infinity to infinity here, which exists because well, that can be shown directly in with the methods of regular calculus, or we're going to see it because the principal value exists through the preceding theorem which we're going to apply. So either way, it's half this integral, and that's 1/2 times what we would get according to the theorem, which is 2 pi I times the sum of the residues. And if we work out the sum of the residues, we can see that this minus 1 goes with this 1, so we just end up with 1 over 4 times root 2 I plus another 1 over 4 times root 2 I with negative signs out front, so that's negative 1 over 2 times root 2 I. The 1/2 and the 2, of course, cancelled. I times I is negative 1, which gives us plus 1, and so the whole thing is pi over 2 times root 2. Okay, good. Well, now we're going to take another sidestep into theory. We're going to talk about something called Jordan's lemma, and we'll see from the formulation why we're interested in it. Jordan's lemma says that if f is analytic at all points in the upper half plane that are outside a circle, z absolute value equals r0, and if we let CR be the semicircle, z equals r e to the I theta, the typical parameterization where theta goes from 0 to pi. And if we suppose that for all radii greater than r0, there is a capital MR, so that for all z on that circle we have that f of z is bounded by MR, and if as r goes to infinity, MR goes to 0, then for all a greater than 0 we have that the limit as r goes to infinity of CR f of z e to the I a z dz is equal to 0. Now that feels horribly technical, but if we're looking, if we're thinking back to the examples that we've dealt with, it actually makes a lot of sense, because what does this thing talk about? It talks about an integral over large circles, and we have seen in the previous example and also in the previous theorem that we want to make those integrals go away. Okay, the only way we can make those integrals go away is if our function ultimately goes to 0. Well, that's not quite true. There are pathological situations where the function doesn't necessarily go to 0, but the integrals will, but those things are something that you'll see in an advanced class, if at all, and it may even be that complex analysis and specifically analytic functions are so well behaved that something like that doesn't happen. So that, however, then means that bounding the function is something that is fairly natural, that ought to happen, and it should also happen that that bound ought to go to 0. Well, because we're integrating over a circle, this bound could go to 0 slower than the length of the circle. So just having the function bounded by something that goes to 0 will not make the integral over these semicircles of f go to 0, but it turns out when f is multiplied with e to the I a z, then it does go to 0. That factor therefore looks a little bit artificial then, but remember that there are an awful lot of functions that have either a cosine or a sine as a factor, for which then the integral here would be the real part or the imaginary part of something that involves an e to the I a z. So that means even though this thing is seriously technical, it is something that that after the fact, once you think about all the pieces, is quite natural. Now let's take a look at how we prove this result. Well, we take the absolute value of the integral that we're interested in, and we push the absolute values inside after we've parameterized the integral, right? The integral would be the integral from 0 to pi of the function, which is all this, and I'll say a few things about the exponent in just a minute, times the derivative of the parameterization, which is I, because the parameterization is e to the I, is r e to the I theta, the derivative will be I r e to the I theta. Good God, that was a rough part here. There's nothing magic happening here. You just write down the parameterization, r e to the I theta, take its derivative, that's what you get, and then you push the absolute value on the inside, and the exponent, of course, will become e to the IA r e to the I theta, which is e to the IA r cosine theta plus I sine theta. Okay, now we realize the function is bounded by mr. The length of the semicircle is r. Well, okay, the part here, the e to the I theta, IR, the absolute value of that is bounded by r, of course. And then we have the integral over the semicircle, e to the negative AR sine theta, because if we're looking at the exponent IAR cosine theta, that's a purely imaginary part. So this is just an e to the IT or something like that, and its absolute value is 1 then also. So all that remains is really e to the I times AR times sine theta, and that's the integrand that we have here. Okay, so we need an upper bound for that integral. In order to do that, we actually go back to drawing the sine function, I think. Namely, we will need something called Jordan's inequality, which says that for all values lowercase r greater than 0, and of course our lowercase r ultimately will be the AR from the previous panel, but for all those guys, we have that the integral from 0 to pi e to the negative r sine theta d theta is smaller than pi over r. Well, what's the problem with this integral? The problem with this integral is this sine theta in the exponent. If that was just a theta or something like that, we'd be looking a whole lot better. Well, draw the sine function and, well, realize that the integral from 0 to pi over 2 will be the same as the integral from pi over 2 to pi, because the sine function is symmetric across the line pi over 2. So one of the things that we're going to do is we're going to just look at the integral from 0 to pi over 2. The other thing that we then see is from 0 to pi over 2, the sine function is greater than this straight line. And that's what we want, because the negative sign will turn that into the negative sign being smaller than the negative of that straight line. And what is that straight line? Well, that straight line goes through 0 and through pi over 2, which means it has slope 2 over pi and a 0 intercept. So this means that from the picture we get sine of x being greater or equal than 2x over pi. And that means that the integral from 0 to pi e to the negative r sine theta d theta is twice the integral from 0 to pi over 2 of the same integrand, which is less than or equal than twice the integral from 0 to pi over 2 e to the negative r 2 theta over pi d theta. And this is something that we can now integrate with a straight u substitution. U equals negative r 2 over pi. And so that means we get that this is, well, this 2 comes from here. The negative pi over 2r is from the u substitution, and then the antiderivative of this thing in here really is negative pi over 2r e to the negative r 2 theta over pi. This is something where you either want to do the u substitution on a piece of paper, or as you're reading this stuff, you can also quickly verify if you take the derivative of this thing, you get the integrand back. Okay, by fundamental theorem of calculus, we have to take the antiderivative and evaluate it at 0 and at pi over 2, which we're going to do. And, well, what do we get? This stuff up front here is negative pi over r. And if we plug in pi over 2, we just get e to the negative r 2 pi over 2 divided by pi, minus at 0, we of course just get e to the negative 0, which is 1. you notice that here everything cancels, and that means that we end up with e to the negative r here, and then the minus sign is pushed in, so this becomes 1 minus e to the negative r. Pi over r is still out front. Well, 1 minus e to the negative r, that's smaller than pi over r because we have 1 and we subtract something positive from it. Okay, so that's Jordan's inequality, which means if we go back to Jordan's lemma, we have the conclusion of the proof: the integral was bounded by mr times the integral of e to the negative ar sine theta d theta, which was bounded by pi over ar. Then the r's cancel and we end up with mr times pi over a, and that goes to 0 as r goes to infinity, because we had that the mr's were going to 0 as r goes to infinity. So that's Jordan's lemma. Let's see how we can handle Jordan's lemma. Well, take a look at this integral. We want to show that the integral from 0 to infinity cosine ax x squared plus 1 dx is equal to pi halves e to the negative a. Again, we have an even function, so we're okay focusing on Cauchy principal values because those will be improper integrals and everything will exist just fine. Well, what do? We take the integral and we realize that it's half the improper integral from negative infinity to infinity. And we realize that that is 1/2 times the real part of e to the iax divided by x squared plus 1. That's a very typical trick to use in any kind of integral where you've got a cosine or a sine. You just represent that as the real part of the complex exponential function. Now we can pull the real part out, of course, so this is a real part of 1/2 integral negative infinity to infinity e to the iax over x squared plus 1. That's the real part of the limit as r goes to infinity of 1/2 times the integral from negative r to r of that integrand. And that is the real part of the limit as r goes to infinity of 1/2 times the integral from negative r to r e to the iax plus the integral over the circle of radius r e to the iaz divided by z squared plus 1 dz, and that is because 1 over z squared plus 1 as r goes to infinity goes to 0, and so here's where we're applying Jordan's lemma, because this integrand is 1 over z squared plus 1 times e to the iaz, and well, that's now a closed contour, so that will be the real part of 1/2 times 2 pi I times the residues, times the sum of the residues of this function in the upper half plane, and there is only one singularity, which is at z equals I, and yeah. And then we're going to use the same thing as before. That is a simple pull, so we're going to well, we're going to cancel the 1/2 against the 2. That gives us the pi I. We keep the numerator, differentiate the denominator, and we plug in z equals I. So that gives us the real part of pi I e to the negative a, because of course I times I gives us a negative 1 there. And we have a 2z, 2i in the denominator. The i's cancel. And we end up with pi halves e to the negative a. And that's already the whole example. Sorry about the skip there. I wasn't sure if something was following. So you can see here how formal argumentation really is connecting with computation, because if you read this computation from left to right, then these are all steps, but it's very mindful symbol manipulation, as a colleague of mine used to like to call it, because specifically this step here is the very important, very good application of Jordan's lemma that says, well, this limit is equal to 0, so we can just add 0. Now we've got a closed contour and we can apply everything else that we have here. Okay, the examples that we've had so far were situations where the singularities were off the real axis. And that is good, because in those situations we just close the contour and apply the residue theorem typically in the upper half plane, but it could also happen, of course, that a pole is on the real line. So let's see what happens when that's the case. When a pole is on the real line and you still want to do an integral, well, you will have the first part of the integral, then you somehow have to squeeze your way around the pole. Suppose that the pole is at the origin, and it often will be in our computations. Then you complete the integral. Then, of course, you want to close the contour. And, well, once you've got that, you've got a closed contour integral. So again, you can apply the residue theorem, and you realize that the integral over the closed contour will just be the sum of the residues inside the contour. You will probably let the larger circle go to infinity and then use something like Jordan's lemma or a direct argument to get rid of that part. But then you also have this tiny circle, and you can't let that tiny circle go to infinity, because then, well, then your improper integral goes away. So you have to let that tiny circle go to 0, the radius of this tiny circle, semicircle, go to 0, and that means that you're getting closer and closer to the singularity, and that means we need to have some kind of result that talks about what happens when you've got a circle around a pole and you shrink that circle to 0. Well, here's the theorem. Take x0 to be a real number and let f be analytic in a deleted neighborhood of x0 with a simple pole, and that's going to be important for our computation. Simple pole at x0 with residue b0. Well, we let c sub rho denote the clockwise, that is negatively oriented upper half of the circle of radius rho around x0, and that's because we already predict that we typically will need the negative orientation, the clockwise orientation here. Then the limit as rho goes to 0 of the integral of f of z over this semicircle c rho that is negatively oriented is negative b0 pi times I, where, remember, b0 is the residue at that pole. Well, let's take a look at that. Because x0 is a simple pole of f, there is a function g that is analytic in a neighborhood of x0, so that f is equal to g plus b0 divided by z minus x0 in that neighborhood, which means we can compute the integral directly. Integral c rho f of z dz will be the integral over c rho of g of z plus b0 z minus x0 dz. And, well, of course, the integral, because this function is analytic, we can apply this analog of the fundamental theorem of calculus for contour integrals. That'll just be the value of g, well, capital G, of the value of the antiderivative. Right. Because g is analytic, it has an antiderivative capital G, and that's what we're going to use, of course, because there is an analog of the fundamental theorem of calculus which says that if you have a contour that is not closed and you integrate an analytic function along that contour, you get the value of the antiderivative at the end point, which is rho, minus the value of the antiderivative at the starting point, which was negative rho, since this thing was negatively oriented clockwise. Plus, of course, we then still have the integral over c rho b0 divided by z minus x0, but that's an integral we can parameterize. So we keep those antiderivatives, and we realize that this integral is the integral from pi to 0, because we're going counterclockwise, of b0 parameterization of the circle x plus rho times e to the I theta, standard parameterization, minus the value x, or x sub 0 here, times the derivative of the parameterization with respect to theta, which is the I rho e to the I theta here. Of course, the x0's cancel, so we keep the antiderivative, we keep the integral from pi to 0, b0 over rho e to the I theta, I rho e to the I theta. Now, of course, the rho e to the I thetas cancel, and that means that, well, we keep the stuff in front, but the integral now is over I b0, and that's a trivial integral. That just gives us negative pi I b0. So that's g of rho minus g of negative rho minus I b0 times pi. And now, as rho goes to 0, g of rho goes to g of 0, g of negative rho goes to g of 0, and those two are the same, so that cancels. And what remains is negative b0 pi I. And that's already the proof for this theorem, and this theorem is of course extremely valuable if we now want to look at an example where we want to solve this integral. We want to show that the integral from 0 to infinity cosine ax minus cosine bx divided by x squared is equal to pi halves b minus a, where we assume that a and b are greater than or equal to 0. Well, then we have the following. We have the situation that we've got a pole at the origin, and that means we have to start our improper integral. Of course, again, we're going to make this symmetric. We're going to start our improper integral somewhere way on the left. We go until we're close to our pole, then we squeeze our way around that with a semicircle, and then we keep going with the integral, and then we close the contour. Same idea as what we had before. And well, we'll call this little circle to have radius lowercase r, so this goes from negative r to r. The outer circle will have radius capital R, so this is negative r and this is r. And we will call the tiny circle S1, and we will call the big circle S2. And superscript plus will be an integral in the mathematically positive orientation, and a superscript minus will be an integral in the mathematically negative orientation, just to be absolutely sure, because we're mixing both of them up here. And so here we go. The integral from lowercase r to r, cosine ax minus cosine bx, x squared dx. Well, that's the integral from lowercase r to capital R of the real part of e to the ix minus e to the ibx over x squared. And that's 1/2 times the real part of the integral from negative r to, that should be a minus r here. And now it is a minus r, so that's 1/2 times the real part of the integral from negative r to r of the integrand plus the integral from r to r of the integrand, because this thing here is an even function still. All right, well, that'll be negative 1/2 times the integral times the real part of the integral over S1 in the negative direction of the integrand, plus the integral over S2 in the positive direction. Let's see, how does that go? The negative sign is basically because I brought this over. If we integrate first from negative r to r, then along S1 in the negative direction, then from r to capital R, and then along S2 in the positive direction, we get a closed contour, and this function doesn't have any singularities inside that closed contour, which means that the sum of all these integrals is equal to 0, and then I just brought these two parts over those semicircles over, and that's what gave us this minus sign out front. Okay, so that means we have to deal with the integrals over these semicircles, and we will. First, we need an estimate for lowercase c greater or equal than 0, and z being a complex number with positive or with non-negative imaginary part. We have that e to the ICZ absolute value is, of course, the absolute value of e to the IC x plus iy, and that would be e to the negative cy e to the ICX, right? You get ICX on one hand, and then you get ICIY, which is negative cy on the other hand, and you just break up the exponential. This thing back here has absolute value 1, so then this is smaller or equal than 1, and that's because y was greater or equal than 0, and c was greater or equal than 0, so you get e to a negative or a non-positive number here. Okay, so that's bounded by 1, but that means that the integral over the big circle, e to the iaz minus e to the ibz divided by z squared absolute value, is less than or equal than what you get when you pull the absolute values inside and integrate against the arc length. But now we realize that on that circle, we have that z squared is r squared, and we have that these two by triangular inequality are less than or equal than e to the IAZ absolute value plus e to the IBZ absolute value, which are both smaller or equal than 1, so this numerator is smaller or equal than 2. Well, 2 over r squared is good, because the arc length of this semicircle is pi r times 2 over r squared gives us 2 pi over r, and that certainly goes to 0 as r goes to infinity. So that large circle actually doesn't bother us at all. If we're then looking at the if we're then looking at the small circle, well, that's where we need to find the the singularity. And of course, that's a little bit dangerous because we're dividing by x squared, which feels as if we actually have a pole of order 2, but that turns out not to be the case, because if we're just looking at e to the iaz minus e to the ibz divided by z, that actually is going to have a limit, which means that's going to have a removable singularity, and that means that the function actually has a simple pole there. So let's first take a look at this. As z goes to 0, e to the iaz minus e to the ibz divided by z, we apply L'Hopital's rule, which works for complex functions in the same way as for real functions. Take the derivative of the numerator and take the derivative of the denominator. So we get ia e to the iaz minus ib e to the ibz divided by the derivative of z, which is 1. As z goes to 0, that ends up being ia minus b, no problem with that. So that means that the residue as at z equals 0 of e to the iaz minus e to the ibz of divided by z squared is the residue at z equals 0 of this function, which is analytic at the origin, divided by z, and that means this residue is the value of this analytic function at the origin. That was one of the theorems we had. And that then means that we get, when we plug in z equals 0, well, we get ia minus b. Yeah, so we got ia minus b. And that means that the limit, as r goes to 0, of this integral over this negatively oriented semicircle of e to the iaz minus e to the ibz divided by z squared ends up being negative ia minus b, which is the negative sign from the theorem. Ia minus b is the residue, times pi I from the theorem, and that actually then gives us that this is a minus b times pi. And well, now we just put it all together. Remember what we have. We had those integrals along the line. We work our way around the simple pole, which actually turns out to be a simple pole, right? And then we go around back, and we know this is negative r, this is r, this is negative r, this is r. We have that this tiny integral goes to a minus b pi. As r goes to 0, we have that the upper integral goes to 0 as r goes to infinity. And that means that the integral from 0 to infinity cosine ax minus cosine bx over x squared was negative 1/2 a minus b times pi, because we had a negative sign from the other thing, right? Because we had to bring this one over, and the 1/2 comes from the fact that we turned this into an integral from negative infinity to infinity. Okay, sure. And that ends up being pi halves b minus a, and that's it. I think the next subject is branch points and branch cuts, but this presentation has gone on for quite a while. Take a break. I'm going to take a break too, and I'm in particular going to let this thing compile so that I'm not going to lose any of the source files here. Thanks a lot. I'll see you in a bit.